Now, when we talk about polarization, right, we usually talk about transverse wave because longitudinal waves cannot be polarized. So what do I mean by that? Now, if you remember your transverse wave, right, your transverse wave, a direction of oscillation of particles, is actually 90 degrees to the direction of travel. So let's say this is a direction of travel. If your transverse wave oscillates this way, this way, this way, this way, they're all 90 degrees one to the direction of travel. So your transverse waves can be in any direction. And usually, if we talk about light waves, let's say coming from the sun, they are unpolarized. That means there will be some waves oscillating this way, this way, this way, all directions. But do you also remember when I taught you about electromagnetic waves? Electromagnetic waves had two components. You had the electric field component, and then you had the magnetic field component 90 degrees to it. Okay, wait, let me draw nicely. Right, but which component are we referring to when we talk about these arrows, right? Usually we are talking about just the electric field, but doesn't mean that the magnetic field is not there. We're just assuming that the magnetic field will be 90 degrees to whatever arrows you have here. That means if this represents the electric field oscillation, there will be a magnetic field 90 degrees to it. But it's too messy to draw both fields. So I'm going to stick to just drawing the electric field. So the electric field is oscillating in all directions, which is 90 degrees of direction of propagation. So what happens is, if you want to polarize, what's the meaning of polarization, right? That means you only want the light to oscillate in one plane. Don't say one direction. Because one direction is either up or down or left or right. That's one direction. One plane means can move up and down like that along the same plane. So let's say you want this light to only oscillate in one plane. Then you need to use a filter, a Polaroid filter, not just any filter, but a Polaroid filter. So we can polarize the light and produce polarized light in any direction. Can be vertical, can be horizontal, can be angle, also can. But how does a Polaroid filter work? Okay, let me just show you the next page. Okay, now when you're talking about a Polaroid filter like this, right? You can't see like slits one. Some people imagine the light is oscillating in all directions, then it must be passing through a vertical slit and become vertical. Now the slits are not possible to be seen one. They're not visible because in the Polaroid filter, I'll give an example, right? If you are you wearing sunglasses, right? There are two types of sunglasses. One is just tinted with ultraviolet filter. The other one is more expensive. It's tinted, got ultraviolet filter and a Polaroid filter. So what is the difference between a Polaroid filter and no Polaroid filter? The Polaroid filter has an extra layer of chemicals, and the arrangement of molecules in that Polaroid filter only allows the vertical component of the electric field of light to pass through. So that means all other components will be blocked. So only vertical can pass through. So but you can't see. You wear a pair of sunglasses, you can't see any lines on whether got Polaroid filter or not. You don't know. But if there is Polaroid filter, the light that enters through your sunglasses will be polarized in one direction. So it will be like vertical. So why they choose vertical, I explain to you also. This is something practical. When you are, for example, driving, and then you notice that the car in front of you, right, has the sunlight, the image of the sun reflected to your eye. So you're driving and then it's a very bright sunny day, and then the image of the sun gets reflected to your eye. Now when it hits the windscreen, right, or the rear windscreen, which is not really flat, not really horizontal, but fairly horizontal, the light coming out will also be polarized, mainly horizontal. So most of the light is horizontally polarized. So you want your filter to be vertical so that most of the horizontal will be cut off. So that means the image of the sun can be mainly cut off, not totally cannot see the sun anymore, but less glaring. Okay, so that's why your polarized sunglasses will help to reduce glare. But if you don't have Polaroid filter, it's cheaper one, that sunglasses. It's only tinted, so it's not so bright, and blocks off UV. Okay, so now let's say you use two filters. So like in this case, let's say the first filter, The light goes in, and this is a vertical filter. The light coming out will also be vertical. What happens to the other directions all cut off already lah. Now then, let's say this vertical filter, you put another filter in front, this vertically polarized light, you put another filter in front, and this filter is horizontal. What will happen is, the vertically polarized light won't be able to pass through. Then what you will see is nothing. So you know how to test your sunglasses, I teach you lah. Let's say the shop wants to sell you some pair of sunglasses, you better get polarized sunglasses, right? But how do you know whether it's polarized or not, since you can't see, right? So you take the sunglasses, right? So this is, let's say, your sunglasses, right? Okay, your sunglasses like that. You put another pair, so as an identical pair, but this time, right, you put it sideways. These sunglasses you put sideways. So that means they are 90 degrees to each other, these two sunglasses. So one will be polarized vertically, one will be polarized horizontally. So if you view from the front, you cannot see anything. But if you rotate it, if you rotate this second one horizontally, so they are like parallel to each other, then you can see. That means if you put the pair of sunglasses in the same parallel to each other, you can see it. Okay, you can see the light passing through. That means you put an object there. Let's say you put a ball, you can see the ball from here. This is your eye lah, you can see. But if you rotate it 90 degrees like this, then you cannot see anymore. Okay, then you know it's polarized. Your sunglasses is polarized. So don't get caught when you're buying sunglasses, because polarized sunglasses are actually more expensive, but it's better for your eyes lah. Okay, so that is called polarization. Now there is another situation like light lah. So this is just to explain further lah. So I told you the light, right, and all types of EM radiation got both electric and magnetic fields, right? So then you can see that if let's say they're all oscillating in different directions, pass through a filter, then you get only one direction. So some people imagine it to be like passing through a slit lah. So if it's your slit is vertical and your light is also vertical, or your waves are vertical, then you can pass through. But if let's say your waves are horizontally oscillating, but your slit is vertical, cannot pass through. But this is just to help you imagine how if your filter is 90 degrees to your oscillation, then you cannot pass through. But of course, this doesn't really happen in your sunglasses. You can't really see the slit, but it's the same principle. Okay, so when you are talking about polarization, two things you need to know now. Longitudinal waves can never be polarized, because your longitudinal waves, right, will be like oscillating parallel to direction of travel. So your wave travels this way, but you also oscillate back and forth, so you cannot select. So this is one of the tests that you can do, right, to see whether your wave is transverse or longitudinal. If they can be polarized, it's transverse. Cannot be polarized, it's longitudinal. Okay, number two is the equation. It's called Malu's law. Malu's law. So what does Malu's law tell you? It tells you that if your light is unpolarized, let's say you pass through the first polarizer first, then what will happen is, what comes out will be already vertically polarized, right? Now, the amplitude coming out, I want to teach you something extra. So it's not in your notes, but you can write down. If let's say the intensity, right, is I here, what comes out, right, will be half of the intensity. So this will be half I already. Now, why half I, right? Because you imagine, right, in the original light is oscillating in all directions. But once you pass through the vertical filter, you cut off all the horizontal. But then some people ask me, what about those diagonal one? What happens? Because vertical can pass through, horizontal cannot pass through. What about those diagonal? Now, those diagonal, right, you have to resolve. Resolve to two components, vertical and horizontal. So those diagonal, once you resolve, the vertical part can pass through, the horizontal part cannot pass through. So we assume, right, that whatever you come in, half of it will be blocked. Because assuming that all the directions have equal intensity, so basically the vertical can pass through and all the vertical components can pass through. The horizontal cannot pass through and the horizontal one cannot pass through, and all the horizontal components of the diagonal one also cannot pass through. So you basically get half I. But this is rare. If they do ask you, you can use this, but this is rare. Okay, but I'm just telling you first, in case you next time need to use it. Usually they will start from here. That means let's say the polarized light is already amplitude A0. Then you use a filter at an angle. So you notice your filter is neither vertical nor horizontal, but it is an angle to the vertical, angle theta. So what will happen is your amplitude that comes out will be A naught cos theta. Okay, this is A naught cos theta. Now, how did they get that? I explained to you. Because if let's say, right, you do a bit of trigo, right? So this is your original amplitude A naught before passing the filter is A naught. And your filter is this direction. Can you see that I can resolve this vector A naught to two components? The component parallel to the filter and 90 degrees to the filter. So if you use a bit of trigo, right, this angle theta, so cos theta is adjacent over hypotenuse, you see. So this component will be A naught cos theta. If you don't believe, you can write down the equation. I show you. If you write down the equation, you'll get something like cos theta is this direction. Let's call this x unknown over A naught. That's why your x will be A naught cos theta. So my point is the amplitude of the the wave emerging after the filter at the angle to the original direction. So you must be this direction, the filter rotated at an angle theta to the original direction, the amplitude will be A naught cos theta. Now that is Malu's law, very simple. Make sense right now? What happened to this component? I cannot pass through because it's 90 degrees to the filter. That's why we don't care about A naught sin theta. Now, we also need to use the equation for intensity. So sometimes they will also include intensity. So let me just shift it up a bit. Now, do you remember intensity is proportional to amplitude squared, right? So we can use back the same equation here for the intensity of the transmitted. That means we know the amplitude coming out is A naught cos theta. What about the intensity of that wave coming out? Okay, no problem. We can actually derive the equation. I2 over I1 is A2 squared over A1 squared, right now. Now, your new amplitude is A, okay, maybe I use capital A, A naught cos theta square over the original amplitude A naught square. Then you can cancel the A naught squared, and then you basically end up with I2 equals to cos squared theta times your original intensity, which is maybe I naught. So that is actually related to Malu's law as well. So in future, if they ask you to find the new intensity, then this is the formula, I naught cos squared theta. But if they ask you to find the new amplitude, then it's just A naught cos theta.